Hello everyone. In this section, we will introduce discrete BJT amplifier circuits, focusing on the common base and common collector amplifier configurations. In the previous video, we finished the discrete circuit analysis of the BJT in the CE configuration. Next, we move to the discrete circuit analysis of the BJT in the CB configuration. As shown in the circuit, the input signal is coupled through capacitor C1 to the emitter terminal, and the output signal is coupled through capacitor C2 from the collector terminal. As usual, we begin with the DC circuit analysis. We need the DC operating point before we can obtain the transistor's small signal model parameters and then perform AC small signal analysis. In DC analysis, the signal frequency is 0, so the capacitor impedance 1 over j omega c is infinite. The coupling capacitors behave like open circuits. Therefore, the DC equivalent circuit is shown on the right. This is the case 4 circuit introduced in the earlier BJT DC circuit chapter, and it is exactly the same as the DC circuit used in the previous CE discrete amplifier video. For AC small signal analysis, the coupling capacitor impedance, 1 over j omega c, approaches 0. Therefore, the AC small signal circuit is shown on the right. At the base terminal, the bias resistors RB1 and RB2 are in parallel. At the output terminal, RC and RL are also in parallel. At the input node, where coupling capacitor C1 is connected, there are two branches. One branch goes through RE, and the other branch looks into the BJT emitter terminal. Therefore, RE is in parallel with RIE, where RIE is the equivalent resistance looking into the emitter side of the BJT. Therefore, we can simplify the circuit. The parallel combination of RB1 and RB2 is replaced by RB, and RC in parallel with RL is replaced by an equivalent output resistance. This gives the simplified AC small signal circuit shown on the right. Next, we substitute the BJT model into the circuit. The resulting small signal equivalent circuit is shown on the right. We again start by finding the input resistance Rin. As before, the input resistance is RE in parallel with RIE. Here, RIE is the equivalent resistance looking into the emitter terminal of the BJT. Using the resistance reflection rule, the base side resistance RB can be reflected to the emitter side by dividing it by 1 plus beta. Then it is added in series with the intrinsic emitter resistance RE. Therefore, RIE equals RE plus RB over 1 plus beta. After obtaining Rin, the input voltage is found by voltage division. Vin equals Rin over Rin plus Rseg, multiplied by Vsig. Since Rin is Re in parallel with RIE, this can also be written as Re in parallel with RIE, divided by the quantity Re in parallel with RIE plus Rsig, multiplied by Vsig. Once Vin is known, the emitter current IE is negative Vin divided by RIE. The negative sign comes from the current direction convention. Then alpha times IE gives the controlled current flowing out of the output terminal. The output voltage is VO equals negative IE times RC in parallel with RL. After substituting IE, VO becomes alpha times Vn over RIE, multiplied by RC in parallel with RL. From the expression for VO, the voltage gain is AV equals VO over Vn, which equals alpha times RC in parallel with RL divided by RIE. When RL is infinite, the open circuit voltage gain is AVO equals alpha times RC over RIE. The overall gain is GV equals Vn over Vsig times VO over Vn, so GV equals Rn over Rn plus Rsig, multiplied by AV. Substituting Rn gives GV equals Re in parallel with RIE, divided by the quantity Re in parallel with RIE plus Rsig, multiplied by alpha times Rc in parallel with RL over RIE. Finally, we find the output resistance Rout. We first set the input signal source Vseg to 0. Then IE is 0, so the controlled current source is 0 and behaves like an open circuit. After a test voltage is applied at the output, the equivalent circuit gives Ix equals Vx over Rc. Therefore, Rout equals Vx over Ix, which is Rc. To summarize the CB amplifier, the input resistance is Re in parallel with RIE. Under typical conditions, Re is much larger than RIE, so Rin is approximately RIE. This resistance is Rb over 1 plus beta plus Re, and it is very small. Therefore, it's a drawback for a voltage amplifier because the input resistance is low. The open circuit voltage gain AVO is alpha times RC over RIE. It has no negative sign, so the output voltage signal is in phase with the input voltage signal. The output resistance is RC. Finally, the CB circuit has good high-frequency response, which will be discussed later in the frequency response chapter. Next, we move to the discrete circuit analysis of the BJT in the CC configuration. As shown here, the input signal is coupled through capacitor C1 to the base terminal, and the output signal is coupled through capacitor C3 from the emitter terminal. The collector terminal is also connected to small signal ground through coupling capacitor C2. Again, we begin with DC analysis. Since the DC signal frequency is 0, the coupling capacitor impedance 1 over j omega c is infinite. The capacitors behave like open circuits. Therefore, the DC equivalent circuit is shown on the right. It is the case 4 circuit introduced earlier, and it is the same DC circuit used in both the previous CE discrete circuit and the CB discrete circuit just discussed. For AC small signal analysis, the coupling capacitor impedance, 1 over j omega c, approaches 0. Therefore, the AC small signal circuit is shown on the right. At the base terminal, RB1 and RB2 are in parallel. At the output terminal, RE and RL are also in parallel. The collector terminal is shorted to small signal ground through capacitor C2, so the AC circuit is not affected by RC. Therefore, we simplify the circuit by replacing RB1 in parallel with RB2 by RB, and by replacing RE in parallel with RL by one equivalent resistance. The result is the AC small signal circuit shown on the right. Next, we substitute the BJT T-model into the circuit, giving the equivalent circuit shown on the right. If the early effect is included, an equivalent RO resistor is connected between the collector and emitter terminals. Here, one side of RO is connected to the collector, which is at small signal ground, and the other side is connected to the same output node as RE in parallel with RL. Therefore, RO is also in parallel with RE and RL. Therefore, we can further simplify the circuit by combining RO with RE in parallel with RL, as shown in the equivalent circuit on the right. We again begin by finding the input resistance Rin. As before, Rin is RB in parallel with RIB. Here, RIB is the equivalent resistance looking into the base terminal of the BJT. Using the resistance reflection rule, the emitter side resistance, consisting of RE in series with RE in parallel with RO in parallel with RL, is reflected to the base side by multiplying it by 1 plus beta. Therefore, RIB equals 1 plus beta times the quantity RE plus RE in parallel with RO in parallel with RL. This can also be derived directly. RIB equals Vn over IB, while IB equals IE over 1 plus beta, and IE equals Vn divided by the total emitter side resistance. Substituting these relations gives the same expression for RIB. After obtaining Rin, the input voltage is found by voltage division. Vn equals Rin over Rin plus R sig multiplied by V sig. Once Vn is known, we examine the current path from the base input through the emitter side to small signal ground. Along this path, Re is in series with the equivalent resistance Re in parallel with Ro in parallel with RL. The output voltage Vo is the voltage across Re in parallel with Ro in parallel with RL. Therefore, by voltage division, Vo equals Re in parallel with Ro in parallel with RL, divided by the quantity Re plus Re in parallel with Ro in parallel with RL, multiplied by Vn. From the relationship between Vo and Vin, the voltage gain of the CC amplifier is AV equals Vo over Vin. Therefore, AV equals Re in parallel with Ro in parallel with RL, divided by the quantity Re plus Re in parallel with Ro in parallel with RL. Since Re is usually much smaller than that parallel resistance, the voltage gain of a CC amplifier is approximately 1. The open circuit voltage gain AVO is obtained when RL is infinite, so AVO equals Re in parallel with Ro divided by Re plus Re in parallel with Ro. Since Re is much smaller than Re in parallel with Ro, AVO is also approximately 1. The overall gain is GV equals VO over V sig, which equals Rin over Rin plus R sig, multiplied by AV. Substituting the input resistance gives GV equals RB in parallel with RIB, divided by the quantity RB in parallel with RIB plus R sig, multiplied by RE in parallel with RO in parallel with RL, divided by RE plus RE in parallel with RO in parallel with RL. When R sig is not large, GV is also usually close to 1. Finally, we find the output resistance of the CC amplifier. We first set the signal source to 0, then apply a test voltage at the output. In the equivalent circuit on the right, focus on the current path from the emitter to the base. Using the resistance reflection rule, the base side resistance R sig in parallel with RB is reflected to the emitter side by dividing it by 1 plus beta. It then appears in series with RE, forming RIE. This resistance is then in parallel with RE in parallel with RO. Therefore, R out equals the quantity R sig in parallel with RB divided by 1 plus beta plus RE, all in parallel with RE in parallel with RO. Since a parallel resistance is dominated by the smaller resistance, and RE in parallel with RO is usually much larger than RIE, R out is approximately RIE. This means the output resistance is very small. Therefore, the CC circuit has a large input resistance, a small output resistance, and a voltage gain close to 1. These are exactly the properties of the voltage buffer introduced earlier for solving input resistance and output resistance problems. In other words, the CC circuit is a voltage buffer amplifier. It is very suitable as the last stage of a multi-stage amplifier. The CC amplifier also has good high-frequency response, which will be discussed later in the frequency response chapter. This concludes the introduction to discrete BJT amplifier circuits, focusing on the common base and common collector amplifier configurations. Please look forward to the next lecture. See you next time. Bye-bye.